Okay, so we'll now begin with the lecture number 12. So welcome you all. So we'll just recap the last lecture. In the last lecture, we looked at what other phases are present in the real systems. So other phases. So we looked at intermetallic phases and various ordered phases that are present, and then we looked at the free energy composition curve profile. So we looked at whether the phases with fixed composition or very little composition tolerances have a shallow Gx curve as compared to phases which have more tolerance for composition fluctuations. So you can have free energy composition curves like this, or you can have free energy composition curves like this, which is determined by the so this is, let us say, G alpha, this is G beta. So this is more of a ordered phase, whereas this is more of a solid solution kind of phase which has larger composition fluctuation, more shallower Gx curve. So this is what we and this is and also that then the transition between ordered and disordered phases as a function of temperature is governed by changes in you can say delta G mix is equal to delta H mix minus T delta S mix, and it is the competition between these two which determines which phase is stable at which temperature. And then we started with our discussion on equilibrium heterogeneous systems. So we introduced two phases, alpha and beta. So alpha is a FCC structured phase. So a pure A has FCC structure, pure B has BCC structure, and they do not have similar structure, which means there is a structural and size dissimilarity. So what we want to see is that how do free energy profiles of these two phases compete with each other to give rise to a phase coexistence. So we saw that we have a scenario like this. So this is Gx curve. So you have one phase with free energy curve like this, another phase with free energy curve like that. So this is, let us say, G alpha, this is G beta. So this is basically G A in alpha, this is G A, this is G B in alpha, this is G A in beta, and this is G B in beta. So we can see that G A alpha is lower than G B beta because the structure of pure A is FCC, which is more stable as compared to BCC, whereas B, being a BCC phase, is more stable in the beta phase form than in the alpha phase form, which is FCC. So as far as this is concerned, this is pure A FCC and pure B BCC. So as you were saying that this pure A phase is FCC structured. So pure A, that is alpha, is FCC structured. The free energy of A in alpha form is lower as compared to free energy of A in beta form. So that is why you see G alpha to be lower than Ga beta. Similarly, Gb beta is lower than Gb alpha, implying that beta phase, BCC structured beta phase is more stable as compared to alpha phase. Now let us look at the phase existence. So what happens in this plot is, now you can see that it is very clear on the left side as you go closer to A, that A is more stable, the free energy of alpha phase is lower than beta phase. If you go to right side, you see that free energy of beta phase is lower than free energy of alpha phase, which is more stable. What happens in the intermediate composition? So that is where the problem is. What happens when these two curves cross over, and what happens in the region which are adjacent to this crossover? So for this, to tackle with this problem, what we do is that, so let me just write it here, okay, for the sake of, so for the purpose of clarity or simplicity, I draw a common tangent between these two curves. Okay, and let us say the overall alloy composition is this. This is my overall alloy composition X naught. Now, this is one composition. You can have another composition of the alloy here, let us say X naught prime, and you can have another composition of the alloy here, which is X naught double prime. So, you can have three alloys, one with composition X naught, second with composition X naught prime, third with composition X naught double prime. Now, what happens for, let us look at first X naught prime, let me label it with different color, X naught prime. So, at this composition, Ga alpha is lower than Gb beta, and the phase that is stable at this composition at a fixed temperature, let us say T is fixed, okay. So, T is equal to T1, okay. So, T1 temperature, X naught prime composition will result in formation of single phase structure, that is alpha phase. So, basically this alpha phase is solid solution of B in A. So, it has majority component as A, minority component as B, and it crystallizes in the structure which is similar to the structure of pure A, that is FCC phase. This continues until this point at which the tangent to the curve G alpha is there. If you go on the right side of the curve now, beyond the intersection of tangent with the G beta curve, in this regime, let me label this as green. In this regime, the free energy of beta phase is lower than the free energy of alpha phase. As a result, the alloy crystallizes in this regime in beta phase structure, that is BCC structured. So, on the left you have alpha phase region, on the right you have beta phase region. So, in this you have alpha, in this you have beta. What happens in the intermediate composition ranges? In the intermediate composition ranges in the vicinity of crossover, so suppose your alloy composition X naught, then what you need to do is that if these two free energy curves are in this, drawn in this fashion, so that they are one is shifted with respect to the other in one region and in another region it is down, then you need to find a common tangent, and we draw a common tangent in such a manner that the point at which tangent touches G alpha curve, if you take the if you draw a vertical line on the x axis from that curve, this is let us say composition X T1. So, we can say that this is let us say X2 T1, okay. These are the compositions within which you will have. So, this line, if you look at free energy of beta phase, this was that, free energy of alpha phase which was that, but the mixture free energy would be this. So, what happens in this case is within this regime you will have a mixture of alpha and beta phase. So, alpha phase of composition this boundary, beta phase of composition this boundary, and these two phases will coexist with each other with lower free energy than either of G alpha and G beta, okay. So, as a result within this composition you have a two phase mixture. So, now let me reiterate it again. When you have these two phases which have overlapping and free energy curves with crossovers at certain places, in this case the principle is to draw a common tangent, and that common tangent allows you to divide the phase free energy composition diagram in various regions, in which you can see which is a single phase region, which is the two phase region. So, what we see here is we see a single phase region alpha below composition X1 T1. So, anything below X1 T1 will be in single phase alpha form. For instance, X naught prime is single phase alpha alloy. Similarly, X naught double prime which is above X2 T1, and in this region alloy will exist in the beta phase form which is BC structured. Between these two ends X1 T1 and X2 T2, which is the solubility limit, which defines the solubility limit of B in A and solubility. So, this is solubility limit of B in A, and this is solubility limit of A in B. So, between these two regions what exists is the phase coexistence of alpha and beta, with alpha phase composition going to be given by this boundary and beta phase composition going to be given by this boundary. So, now let us, so what we do here is basically if you look at the free energy profiling, the free energy drops from this point. Let us say this is G naught beta, this is G naught alpha, and what you have here is G equilibrium. The equilibrium free energy is lower than G naught alpha and G naught beta. So, for any composition, if you draw another composition, for instance here, if you draw for this region, all of them will show a decrease in free energy from here to here, here to here, here to here, and then here to here. So, your free energy is given by free energy lying on this line. Okay. And another thing which this curve shows you, if you extend this further, the intersection of this line, what does it tell you? The intersection of this line is basically the chemical potential. So, this is for instance mu A, and this is for instance mu B, and thus, so what this tells you is that you have chemical potential of A on this side, you have chemical potential of B on this side, and since you have a common tangent to G alpha and G beta, what it means is that chemical potential of A in alpha is equal to chemical potential of A in beta, and chemical potential of B in alpha is equal to chemical potential of B in beta. So, now let us now look at how does the activity vary, because activity is a signature of chemical potential, activity variation. XA. So, if I draw now two phases, so let us say this is G alpha, this is G beta. So, G alpha, G beta, the two phase equilibrium is given by the common tangent. So, this is, let us say, alpha E, beta E at temperature T. Okay, T is constant. So, let us say T1. Okay, and the so if you now look at the, for example, you want to look at the variation in activity, you need to draw a common tangent. So, for common tangent, let us say I take this particular point. Okay, let me use a different color. So, if I now determine what is the, so this is basically the chemical potential, right? This is G A alpha, this is G B beta, this is mu A alpha, and this is mu B, this is mu A, let us say, and mu B. Okay. The differences between this is minus RT ln A, and difference between this is minus RT ln A B. Now, so this is what is the activity say. So, if you now draw the activity profile, so if you draw the activity profile, So if I draw, so let us say corresponding to these two figures, so this is alpha E, this is alpha beta. So this is A, this is B. So I draw two vertical lines. So this is alpha E, this is alpha beta. So let us first draw AB, activity of B. Now activity is same as chemical potential. So what it says is that within the, so we know that in this you have alpha, in this region you have beta, then in between you have alpha plus beta. So what it says is that the activity of pure A, of course, so when you have pure A, activity of B is equal to 0. When you have pure B, the activity is equal to 1. So this is the top line. Okay, so this is the top line which says activity is equal to 1. In between, the activity of A, activity of B in alpha must be equal to activity of B in beta. So we want to say that chemical potential of A in alpha is equal to chemical potential of A in beta. Similarly, chemical potential of B in alpha is same as chemical potential of B in beta, and that is what it means in terms of activity. The activity of A in alpha is same as activity of A in beta, and activity of B in alpha is same as activity of B in beta. So chemical potential of each of the element in respective phases must be equal. That is, mu A alpha is equal to mu A beta, and mu B alpha is equal to mu B beta, which implies AA alpha is equal to AA beta and AB alpha is equal to AB beta. So if I now plot here, so since the activity, so this is the AB alpha is equal to AB beta, and in other regions it goes like this. So this is the variation of activity. Similarly, when you plot the activity variation for AA, again you have to draw these two lines, alpha E, beta E. So again you will have a region in which A alpha will be equal to AA beta, and now for pure A it would be 1. So it will start from 1. So this is AA here, and then it will go through a plateau, and before it goes to 0 in this regime. So this is how two-phase equilibrium will be. So for multi-phase equilibrium, you can say that mu I in A is equal to mu I, so mu I alpha is equal to mu I beta, mu I gamma, and so on and so forth. So this is how the chemical potential equality has to be maintained across the free energy landscape. Now let us build a phase diagram now. Okay, so we now go to building a phase diagram based on this free energy composition concept. So we have said that the free energy, so we have said that chemical potential must be equal for each element in two different phases, and that is obeyed by activity as well. Okay, so basically now let's look at an alloy system AB. It is an ideal solution. So, A and B are miscible in each other in both solid and liquid states. Okay. So, first what we should do is that, let us say at constant temperature and pressure, okay, stable form of so in the solid state, of course, pure A is, let us say, FCC, and a stable form of pure B, let us say, is also FCC. So, this is something which is very well obeyed by, let us say, copper nickel system. So, it is ideal solid solution that you make. So, they are miscible into each other, both liquid and solid state. The melting point of A is TMA, melting point of B is melting point of B, and let us say that TMB is lower than TMA. Okay. And let us say the free energy of solid is GS, free energy of liquid is GL. Okay. And we know that free energy variation, free energy of solid goes like that, free energy of liquid drops even further. So, this is GL, this is GS, and this represents what we call it as a melting point. So, this is true for both alpha and beta phases. This is G, this is T. So, free energy of solid decreases, free energy of liquid decreases, but free energy of liquid decreases much more sharply as compared to free energy of solid. So, now let us look at, so when you plot the free energy of solid and liquid phases, they are something like this. So, this is GL, and this is GS, fairly similar curve. GL is GS is more you can say shallower as compared to that. So, this is XB and this is GS. Now, it is the relative movement of GL and GS with respect to each other that will determine the stability of various phases. So, let us first look at a temperature T which is greater than Tm of A, which is greater than Tm of B. So, this is T1. So, in this regime, this is A, this is B, XB, and this is GB. So, what we say in this phase is, we say that G so, in this phase, when the temperature is higher than the melting point of A and B, the free energy of liquid has got to be lower than free energy of solid. As a result, this is GL and this is GS. So, this is GA L, this is GAS. So I'll just make sure subscripts are written above. So this is GS, this is GL, this is GBS, this is GBL. Okay. So this tells me that all throughout the range liquid is stable. So which means liquid stable at all x b. Now let us come to second scenario where there is a temperature T2 which is equal to melting point of A but is bigger than melting point of B. Okay. In this scenario, again let us draw the free energy curve. So when the melting point, when we are standing at the melting point at Tm, we know that Gs is equal to Gl. So which means for A, this is A, this is B. For A, the free energy curve will be coinciding. So this is Gs, this is Gl, this is Tma. At this point, Gas is equal to Gal, and this is Gbs and this is Gbl. Let us say this is point A. Okay. We again see that nearly for all compositions Gl is lower than Gs, but at pure A, Gl is equal to Gs. Let us move to another point, T3. T3 is now lower than Tm of A, but it is bigger than Tm of B. So at this point, what will happen is, so this is G. So now at this temperature, we are at a temperature which is lower than melting point of A, which means for A, solid phase is more stable as compared to liquid phase, whereas for B, the liquid phase is more stable as compared to solid phase. So now these two free energies, as you can understand, they will start crossing with respect to each other. So if you plot, so this is, let us say for this is, let us say for solid. Okay. Now for solid, this is GAS, this is GBS. So solid free energy now has to be lower than the liquid free energy for the A. So which means the other free energy curve will start at this point and it will cross over this curve somewhere here, such that Gbl is lower than Gbs, but Gal is higher than. So you can say that, you can see now in certain region your solid free energy is lower than that of liquid free energy, whereas in the other parts your liquid free energy is lower than the solid free energy. Let us now take it further at T4. So T4 is greater than T3, T4 is smaller than T3, but is still bigger than TMB. So what we do is that in this slide, we draw now a common tangent. So using the same principle that we applied earlier. So this is the common tangent. So let us say this is XS T3 and this is XL T3, okay, and this point is point B1 and this is point C. So what we will do is that now we will stop here. We'll do the further analysis in the next class. But what we have seen in this class is we have learned how to draw free energy phase diagrams for. So if I come from the beginning, what I said was when you have two phases with different structures, these phases will have overlap of free energy curves in such a fashion, so that on one side you will have one single phase region, on the other side you will have another single phase region, in between the relative shift of these free energy curves which will determine what phases will coexist with each other. And then we said that for two phase coexistence the mandatory requirement is that chemical potential of each of the element in respective phases must be equal, that is mu A alpha should be equal to mu A beta and mu B alpha is equal to mu B beta, and that is obvious from the tangent that is drawn from this line. So the common tangent says that this common tangent is nothing but the chemical potential, and this says that the chemical potential of A and B in two phases, A in two phases and B in two phases must be equal. Okay, so we'll stop here. Thank you.